Hi there, and welcome to another lesson in BCIT's Technology Teacher Education 4010 class, where we take a quick introduction to, computer programming through the eyes of the Arduino. And we use a few other tools on our way. But last day, we actually downloaded the Arduino IDE, or Integrated Development Environment, and put it on our computers, and took a USB cable, plugged it into our Arduino, and wrote some code to blink some LEDs, and uploaded that onto our Arduino. And when the code came into the Arduino, it came in through a chip right here that handled all the communications with USB and got stored on this chip right here, which if you look down at it really closely, you can see is an Atmega. And in this case, mine says Mega 328P. I suspect you'll see similar writing, if very faint, on your Arduino. If you don't, it's probably not an Arduino. Now, the chip might look a little different. You can see over on this side that there's picture of an Arduino um, with a dip version of the chip on it. This is a surface mount version of the chip, and there's a dip version of the chip. That one will also say Atmega 328P. They're the same chip, just the surface mount ones are packaged a lot tinier than the dip chips. Dip, short for dual inline package, and that describes that whole category of traditional integrated circuit chips that we can solder into boards by putting the pins through holes. So dip chips are a through-hole device. Anyway, we're here to talk about coding, not soldering things up right now. And so last day we were able to make the world's most complex Winky, well, not the world's most complex Winky Blink, but an unnecessarily complex Winky Blink by writing code to the Arduino and turning pins 9 and 10 on and off really rapidly. And we started out by doing that on the TinkerCAD circuit simulator. And I really like developing my code and simulating it where I can on TinkerCAD circuit simulator. So let's see right here. And I'm just going to shrink myself down and pop myself in the bottom corner so I'm not getting in the way of stuff here. And hi, here I am down over here. Okay, now we've got a nice big screen view of the TinkerCAD circuit simulator. And go ahead, log into TinkerCAD. You'll probably find your code sitting there from last time as well as your circuit. We're going to use the same circuit. If you've lost the code or if you didn't get it finished last time, a couple of things to note that we've got this logged in and hooked in right here, pin 9. Okay, right here comes up to an LED. You can get your LEDs by, let me just get rid of that code window, digging down in right here. We've got LEDs and resistors right here, and you can change the values of your resistors by clicking on them. And I've set that to be somewhere around 280. And when you change the value, the resistor color code changes too, which I think is really, really awesome. Okay, so go ahead and get that set up. Keep in mind that we did some good breadboarding technique and used red wires for our power supply and black wires for our ground, and then we hooked the two sides of the breadboard up together. Okay, so you may still have that up and running, but if you don't, go ahead and pause the video now and go ahead and get this hooked up because we're going to do a quick review of what we did last day, and then I'm going to talk about something new, the AnalogWrite command. And once I've done that, I'm going to beat you over the head a little bit with some binary math. So if you've got that, you'll done that in the past, you'll find a place in the video where you can put me on 2x speed and listen to me talk like a chipmunk, or just forward past it. And then we're going to introduce you to the for loop. But before we do any of that, let's go back and take a look at some of the code we wrote last day. Okay, and here comes the code out right now. Now I've got blocks plus text turned on, okay? And I really like using the blocks plus text mode. And let me stop the simulation right here. If the simulation's running, you can't change anything in here. But in the blocks plus text code, you can change that to get just blocks or just text. Later on, we will be doing just text, but while we've got the blocks working for us, I want to use that to take a look at some of the things that go on inside the code because it really helps you visualize what's going on. It also helps prevent spelling errors and a whole bunch of things like that, which can be frustrating when you're starting out. More frustrating when you're very experienced, but at least you know how to solve them. Okay, so right here, we've got some blocks saying what's going on inside of our code. And it says set pin 9 to high. There's pin 9 right there. Okay, now when we say high, what we mean is 5 volts. So the Arduino right here is getting a 5-volt power supply coming in from your USB port because USB runs at 5 volts. So the Arduino has this nice 5-volt power source, and you'll notice that we've got a 5-volt pin right here, which is great for powering all sorts of devices. And so when we set pin 9 to high, this pin 9 on your Arduino actually trickles back through a little piece of copper on the printed circuit board and comes back to one of the pins on your chip. Now, I can't remember which one off the top of my head. You can go ahead and look up the Arduino schematic and figure it out. It's all open source, but it doesn't really matter. We just call it pin 9 when we're working with the Arduino. And what we're doing is inside this chip, we're flipping a transistor, okay, turning this pin so that it's connected to 5 volts instead of being connected to ground. It's not that big of a deal. It's just changing a transistor. And we set pin 10 to low, okay, putting a transistor on that connects it to your ground side, which also comes from your computer. So that's all that those two commands do. We wait for 0.1 of a second. Now, I think we might have said 1 second last time, but we sped it up a little bit, and I'll talk about that when we take a look at the code over here. And then we come along and we flip it and we set pin 9 low, pin 10 high, so that we change their states, and we wait, and then this code keeps on looping forever. So when we take a look at our code over here in the text, and it's important to start getting an appreciation for how the code looks in the text. We talked about some of the structures of an Arduino text-based program. And so you'll have void setup right at the beginning. It's really important that every Arduino program has a void setup and a void loop in it. Now, you can have other void routines, and just like in VexCode VR, you wrote your own routine. So you could have a void circle routine down beneath here, and you could access that from void loop. You could come down here and you could run your circle routine and go back to void loop. That's fine. You could call it from your setup routine and come down here and run it and come back here and then go into your void loop. And loop, as the name suggests, is what's going to run forever and ever, or at least until the Arduino loses power. So setup, this code runs once. Loop, this code runs until you turn the Arduino off. It just keeps going over and over and over, as the name loop would suggest. Now, how does it know how to break things down and what is setup and what's in loop? Well, that's where these squiggly brackets or ellipses come into play. And they're kind of giving it the big hug. We had some statements in our drag and drop programming where we had a whole bunch of commands held in a big orange hug. Well, these are the big orange hug of the text world, okay? And that means that everything between this opening bracket and until it sees a closing bracket is going to be governed by void setup. Now, these are the squiggly brackets, the ellipses, distinctly different from the round brackets, or for that matter, the square brackets. But you can see the squigglies used time and time again, right up here and right down here, and loop is all held together that way as well. Okay, so in here in setup, now the first thing that happens in setup, and keep in mind setup is exactly what it says. It's telling the Arduino how you want it to be set up. And we have this command that says pin mode. Now this doesn't show up in your drag and drop because it's a little bit complex. They're keeping drag and drop easy. But it's going to be more useful as we get into the text-based programming and doing more sophisticated work, because what you're doing is you're giving the Arduino a heads up that pin 9 is going to be used as an output. Because pin 9 can also be used as an input. You can use this to control things in the real world, or you can use it to read things that are happening in the real world. And that's something that we're going to talk about a little bit later on. But you can use it to read things, or you can use it to write things. It can be an input or an output. A couple of different states for that pin. All right, since we've said it could be an output, that means that we're going to control it with a digital write command. And so these little brackets here, the round brackets that come after each of these statements, this is how we pass variables to functions or routines. The digital write routine, or the delay routine right down here, is just a subroutine. Now, you don't see that subroutine as part of your code because somebody's already written it and included it in the language. But just as you created a circle subroutine when you were doing VexCode VR and you passed it a variable called radius, well, if you'd had your circle routine baked into VexCode VR, other programmers wouldn't see the circle routine either. They'd just type in circle and the radius, and the little robot will go out and do a circle. In here, you don't see it, but these variables are being passed to the function, and they're telling the function what to do, which is essentially make pin 9 go high, make pin 10 go low, wait for 100 milliseconds, okay, 1/10 of a second. If we wanted a 1 second delay, the command would be delay 1000. Then we get digital write, we swap it around, come to our end closing bracket, and it goes back, and it loops over and over and over again, and that's why these lights are still blinking. So there we go. Quick review of the program that we had going on before. Now, it's nice that we can turn them on and off, but quite often people don't want something all the way on or all the way off. It would be nice to be able to fade something in or fade it out or have a light on dim because gosh, it's awfully bright when you blast an LED straight into your eye. And for that, we need to take a look at another command. And that command is the AnalogWrite command. So let's take a look right here and let's just get rid of, you know what? Let's get rid of all of that. Poof, it's gone. Okay, and notice it all disappeared out of our text window as well. If you're not getting the text as well, remember that's blocks plus text right up here is what you want. Okay, so what we're going to do now is we're going to take a look at a command called AnalogWrite. Now, in here, it doesn't say AnalogWrite. In blocks, it just says set pin 3 to a number. And I don't know, let's choose 50. And then we're going to come down here and, oh, we don't want pin 3. We want pin 9. Set pin 9 to 50. Set pin 9 to 255. Okay. Now, this code isn't going to do anything useful for us right now because it's going to run so fast that we'll be setting it to dim and we'll be setting it to bright. And we won't actually see it do anything because we need to come into our control. I'll put a little bit of a wait in here. Let's wait 0.1 seconds because it's boring to wait for a whole second. I'll wait for 0.1 seconds. Okay, and let's start that simulation. And our orange LED is flickering back and forth right here. And you see sometimes it's bright and sometimes it's dim. Okay, but it never quite goes off. It does, however, go on to its full brightness because I set this to 255. Now, 255 is a very important number in computing. And the reasons for that may not be immediately apparent. But I'm going to grab a sheet of paper here. And so long as I remember to turn the camera on this time, I'm going to explain why that matters. So, note to self, when using notepaper, turn on the camera that lets people see the notepaper. There we go. This camera right over here. and make it big enough so that people can see the note paper. There we go. So move that one out of the way, and let's replace it with something a little bit more traditional, a piece of note paper. Now, when we're talking about numbers inside computers, they're actually really simple. They're just a little different from what we do every day. So if you haven't been thinking about computers every day and how they work inside and how they store data, well, it's going to take you a little bit to shift your head around so that you can wrap your head around how computers store data. And once you do that, you'll be like, yeah, it's simple, it's pretty boring. So let's take a look at what's going on and we're doing a digital write command. Keep in mind, computers are binary devices, okay? Binary means on or off, and so those two values are often represented as 1 or 0. 1 representing on, 0 representing off. Now you also just saw in the digital write command that we had two other words used to describe these. We had high, and yes, it is all capitals, and low. Okay, and each of these things means the same thing to a computer. So 1, on, and high, all in an Arduino, means 5 volts. 0, off, low, or, in the case of the Arduino, ground, all mean the same thing. And that's because the way we store memory in a computer. Computers were designed to store data in binary chunks, on or off, the quickest, simplest way that you could store data. And that comes back to the early days of computing. And you think about some of the early card punch, hole punch machines, there was either a punch in the card or there wasn't. Okay, they didn't mess around with how big was the hole, was the paper brown. They're not worried about things like that inside the early computers. They just wanted to know, was there a punch in this location or was there not? That was one way to store data. Now, as things went on, they got a little bit more sophisticated. And let me just flick this over here. And if you want some time, come into my office and ask me to show you some magnetic core memory because my high school electronics teacher gave me a couple of pieces of core memory out of a computer from the 1970s. And what's really cool is that when you look at it, it looks like this. Now, I've got much larger pieces of core memory. So this core memory right here was 32 by 32 and could store 128 bytes. We'll talk about what bytes are later on. But we'll take a look at that. You know, mine's a lot bigger, but man, this stuff could not store memory in very tight spaces because if you look at it up close, this is what it was made up out of. Actual physical magnets. These are little round rings right in here, and they are held together on this intricately woven set of very, very fine electrical wires. And so ask me to take a look. We'll get the magnifying lens out. I've got actually some really nice digital magnifying scopes, but you can actually see these unaided with normal vision. But they look so much more spectacular when you zoom in and get a really good close-up because they do look like this, and somehow there was a machine that put them all together. Kind of wish someone had saved that machine and just used it to weave fabric now, because if they'd used slightly stronger wires and put these little beads over top of it, I just think it would be really cool fabric, but that probably tells you more about my fashion choice than what would sell in the runways of Paris these days. So anyways, that's core memory, and each of those magnets could be magnetized north or south. And you magnetize it or not magnetize, and you're able to go in there and sense whether it's magnetized or not, and then you'd use two wires to send a big blast of current through it and change its magnetization state. Now, as computers advanced and technology got more sophisticated, the transistors started to come in here and take the place of those little cores. And if you go to falstad.com/circuit, it's important that you add the /circuit, falstad.com/circuit. You'll come to one of my favorite online circuit simulators. And inside there, if you come to the circuits that Falstad has prepared for you, you can come down here and under transistors, you can come down to multivibrators. Always good to give your grade 9s a chuckle. And you come down here and take a look at the bistable multivibrator, also known as the flip-flop. Very significant circuit in electronics. And this is what that circuit looks like. You've got 2 transistors in here, along with a few different resistors. Now, when the circuit starts out, you've got 2 pins down here that you can control, set and reset, and 1 output right here. The output is where you come to see what the value of the transistor is. It's either high or low, because if this transistor is conducting, then electricity comes through this resistor and flows down to ground, and really this value is very close to 0 because the electricity is all flowing through that transistor right there. But if you set a bit right here, now notice I just clicked that briefly and I just momentarily hit it, and I keep hitting it, nothing changes over here. What happens is when you set that one high, that turns this transistor on. Well, now electricity can flow down through that way, okay, which turns this transistor off, because now there's no electricity flowing down this way. That puts our output to high, because with no electricity flowing down this way, this pin has no, well, it's got a high valued resistor, it's got electricity has nowhere to go, and this pin essentially becomes high. Now it's not the full 5 volts coming in, but it's close enough to give a high signal that could be used to trigger another flip-flop circuit somewhere else. So you get these chains of them all coming together. Now, you're thinking the transistors that we use to make your Winky blink, and in fact, if you look at this circuit, it's not so different from a Winky blink. It's just there's no capacitors because we don't need to time anything in here. We've got this circuit right on here, and we're getting a high output coming off here. The big transistors that you're used to looking at in your Winky blink, of course, get shrunk down onto microchips, and we can fit millions and millions of transistors onto microchips, so we can store huge amounts of memory in tiny little microchips now. There's different types of memory cells, okay? And you've heard of flash RAM and ROM and EEPROM are some of the words that are out there. Over the course of the development of the computer, there have been many, many ways developed to store a bit of information, and core memory and the flip-flop are just 2 of them, and neither of those 2 are actually used all that much in the high-end computers nowadays. People have gone faster and farther, but this is why transistors are so important, and also why the bit is so important. So a little bit of computer history in there explains some of the places where we're at and why binary counting is so important to us. Now, let's take a look over here, and let's turn this camera back on and make sure I hit the transition button so you can actually see what I'm writing this time. Yes, this is my second try at this video. Apparently the lesson goes better when you can see what I'm writing. Now I wanted to take a moment to explain why that 255 number was so important and why you're going to see it again. If you've done a lot of binary counting and you've maybe explained this to people yourself, feel free to put me on super speed here and until you get to the boring part, or well, the next boring part, but you can skip over this. If you haven't done much binary counting for a while, let's think about how our human counting system works. Okay, and we use what's called a base 10 system because we have 10 fingers and we can go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And when we get to 10, we actually do something really special that's really important to your understanding of binary. So let's put those digits down and take a look at how base 10 actually works. So we've got this number called 0. No fingers are up. Okay, then we can go 1, 2, 3, 4, 5, 6, 7, 8, and 9, and there's nothing special all the way up to 9. We've just got different symbols representing what's going on. Okay, but when we get to that last finger, when we get to the 10th one, something special does happen. We say, hey, that's one full set of hands and no additional fingers. We put a 1 in the tens column and a 0 into the ones column now. When we get to 11, we've got one full set of hands plus 1. And if you've got a number like 37, that means you've got 3 full sets of hands plus 7 additional fingers, a clear sign that genetic modification has gone too far. Sorry. All right, binary numbers work exactly the same way, but computers don't have 10 fingers. They've got 1 bit. And so 1 bit is really easy to do 0. Well, you've got 0. And it's really easy to do 1 because you've got 1. But if you try to express the concept of 2 using binary numbers, what we know in decimal counting or base 10, in binary or base 2, we don't have a way to express that. Excuse me. What we need to do is say we've ran out of all our digits, we've used up that bit, so we've got 0 in the bits column and a 1 in the twos column. We've used up all our bits once. For a 3, well, we've used them up once, plus we've got 1 extra. For a 4, we've used up all the ones in there. For 5, we've got 1 in the 4 column, nothing in the 2 column, and a 1 in the ones column. For 6, 1 in the 1, 1 in the 2, nothing in the ones column. And for 7, we've got 1, 1, 1, 1. And for 8, we've got 1, 0, 0, which gives us 8. Now, this is what we call a 4-bit number because it takes 4 bits of information to store it. What's the biggest possible 4-bit number that you could get? Well, the biggest possible number would have a 1 in the 4 column, or sorry, 1 in the 8 column. What am I saying there? I'm getting ahead of myself. We just said that was the 8's column. A 1 in the 4 column, a 1 in the 2, and a 1 in the 1. And if you add that up, 8 plus 4 is 12, 13, 14, 15 is your biggest possible 4-bit number. Now, this is also of historical significance because early computers were only able to process 4 bits of information in one step. They were what we called a 4-bit computer. So they could process larger numbers, but it would take them multiple steps. So in order to process anything bigger than this, they'd have to process one 4-bit number and store it, go get the next 4-bit number, put it together, and it would take multiple steps to get that number out. No, it would be slower, it would take time because their CPU was a 4-bit CPU. It maxed out at 4 bits, and it couldn't handle numbers larger than 15 without doing multiple steps, which caused things to slow down. So people wanted to get more powerful computers. and they did a whole bunch of things, but as they were eventually able to pack more bits onto a chip, they came up with an 8-bit processor. And the 8-bit processor was enough that they could do all sorts of really interesting things with it. And the 8-bit processor was around for a long time. The Apple II, the Commodore 64, the Commodore PET, the TRS-80, all of those groundbreaking home computers of the early of the late 1970s, early 1980s were all 8-bit computers. And your Arduino has an 8-bit processor as well. The 8-bit processor has really formed the groundwork for a whole range of electronic devices because it's just big enough to be really useful. These 4-bit processors didn't quite have enough processing power, but as soon as you got into 8 bits, well, you could process larger numbers because you could process at one time a 1 in the ones column, a 1 in the twos column, a 1 in the 4 column, a 1 in the 8, a 1 in the 16, a 1 in the 32, a 1 in the 64, and a 1 in the 128 column. There's my 8 bits that could be processed in one processing step. You could process the number 11111111, right? And that, if you added it all up, came out to 255. Now, why was this such a great groundbreaking number? Well, think about the characters in the English language. We've got 26 letters. So you'd think they could have stopped when they got to like something that could hold 32 different values. But then there's capital letters, and you need to be able to differentiate the capitals from the lowercase. So now we're up to what, 48 different characters. Oh, but then there's all the numbers. So now we're up to 58 characters. Oh, but there's all your math symbols and your exclamation marks and punctuation marks. So now you're starting to get up to a significant number of characters. And what they found was that in order to have at least basic communication, you needed to have at least 127 different values, which meant that you could have got away with a 7-bit number. But because of the way computers work and the way that they like to do things in binary units, just like we like nice round numbers, okay, 7's not a nice round number in binary. 8 is a nice round number in binary. Okay, so we like numbers like 10, 100. We based the metric system on nice round decimal numbers. We've based our computer CPUs on nice round binary numbers because they work great and they're easier to design. And there's no point designing a 7-bit CPU because it's trivial to design. Actually, it's probably easier to design the 8-bit CPU to make it work. So that's why we have the 8 bits forming 1 byte. An additional piece of trivia information is the 4-bit computers used a 4-bit memory location, and they did not call that the byte. They called it the nibble, because a nibble is smaller than a byte, but bigger than a bit. Somebody had a sense of humor. Anyway, where the Y came from? Why ask why? Okay, so here we go. We've got this 255, which, after watching all that, you're going to remember is a very important number. The other thing that you've probably picked up from this is you've watched this and you have just deciphered Nintendo's numbering scheme for all of their game consoles. The Nintendo 16, 32, 64, and the 128, all based on their processors. I mean, it makes sense, right? Why wouldn't you do it that way? So there we go. We've got this AnalogWrite command, and the AnalogWrite uses an 8-bit number because the Arduino can process that 8-bit in one easy chunk. It's digestible. Your computer that you're watching this on is probably a 64-bit computer. And so even though it can process 64 bits in one quick chunk, and 64 bits just results in a massively huge number, okay? So an 8-bit number right here, This number is 2 to the 8 minus 1 equals 255. Okay, to get an idea of what your computer can process in one chunk, try 2 to the 64 minus 1. I'll leave you to do it. That's the largest value your computer can process in one chunk, and the number of possible different characters that it could store in one memory location if it broke it down that way. Strangely, we still use 8 bits as the basics of our computer memory. We talk about the byte because it's such a useful value and it stores approximately 1 character of information. In fact, you'll sometimes see a byte also referred to as a car-sized variable because it's really handy for restoring 1 character, including numbers, exclamation marks, punctuation marks, capitals, accents, and a whole bunch of other things. There is another naming scheme for keeping track of characters, and that's more common, and that's why you start to see different languages being included and more symbols and all sorts of things showing up that way. But let's go back to TinkerCAD and turn that screen off right there. And here we are over in TinkerCAD, and there is our 255 right in there, showing up nice and clear. The biggest number that you can store there, which means that's the brightest that you can make that LED. Now, when we're turning these on and off, what we're actually doing is something called pulse width modulation. It's not true analog. The Arduino pin is always either on or off. We don't have a true analog value coming out here. What's happening is divide the time slot, okay? Divide a second up into 255 units. And if you put an analog value of 1 into there, the Arduino will be on for 1 and off for 254. If you put 50 in here, the LED will be on for 50 and off for 205. And if you put 255 in there, then the LED is on for all 255 of those time divisions. Now, cram those time divisions down into something much, much less than a second. Do this about, I think it's 6,000 times a second. And all of a sudden, the Arduino is turning that pin on and off so quickly that you can't see it doing the turning on and off. What your eyes see is the average number of photons coming off of that LED because the LED is going, hey, I'm on, I'm off, I'm on, I'm off, I'm on, I'm off. But you can't pick that up because it's going so darn fast, just like a movie. So although we call it AnalogWrite, it's a little bit of a cheat. It just looks like an AnalogWrite to our eyeballs, which when dealing with LEDs is good enough. Okay, so I told you that one of the reasons we wanted to do an AnalogWrite was so that we could fade our LEDs in and fade our LEDs out. Okay, now in order to do that, you need a routine that starts the LED off dim and then makes it brighter and brighter and brighter and brighter to fade it in, or starts it off bright and makes it dimmer and dimmer and dimmer and dimmer to get it to fade out. And thankfully, there are commands to do that. And let's clear some of this up right here. In fact, I'm just going to get rid of that right there. Oh, I hope I remember to press mute that time. Okay, so what we're going to do is we're going to get pin 9 to fade in. Okay, and to do that, we're going to use the repeat command. Okay, and when I put the repeat in here, you can see that we've hugged this command right here. Okay, And you can see that our code over here has now shown up with a few interesting things. It has a variable, okay? And the variable is a type of variable that's called an integer. Now in the Arduino, the integer variable is a variable that uses 2 bytes of data to represent a number. Okay, so 2 bytes of data gives us 16 bits. This means this is a 16-bit number, and that means it can store about 32,768, I think, different values. So um, we've got this variable in here called a counter. And it comes down here, and then we come in, we set our pin mode. So we're telling pin 9, hey, pin 9, you're going to be an output. And then we come in here, and our loop routine runs for quite a while. Now, these squiggly brackets right here control the loop routine, but these squiggly brackets right in here control the for statement. Now, a for statement is a really interesting statement, okay? Now, in here it just says repeat 10 times, but let's take a look at how it does the counting, because in order to repeat 10 times, it obviously needs to know, hey, is this the 8th time around, the 7th time around, or the 6th time around? And so right here it says for counter equals 0, okay? So the for statement has this format where it says I'm starting with 0. Now you could use any variable in here. If you're typing it in, I don't tend to use big words like counter unless I really need to. I'd probably say for x, and I'd have int x right up here because that saves me writing a whole bunch of characters. But we use counter. You could call it Bob if you wanted to. Um, so for counter equals 0, okay, semicolon to break that statement up. Now the next statement in here is how long do I keep doing this? And the computer will keep doing this while counter is less than 10. Okay, and this statement tells it how much counter is going to increase by each time it loops through here. So it's going to increase by 1. Now, plus plus counter is a fancy way of saying counter equals counter plus 1, which is the command that we used in VexCode VR when we kind of had to hand code this in there. Okay, so this is coming through right here. And then we've got this command that says AnalogWrite 9, 50. Well, nothing's going to change in here. What we want to do is we want to start at 0, and we want to increase the brightness of the LED to its maximum, which is 255, the biggest value that you can put into 1 byte. Then what we want to do is we want to set this, and let's see, does it let us access? It doesn't let us access that variable counter. Does it come down here? Will it let us create a variable called counter? There we go. Oh, that little cheat. It changed this to counter 2. There's some things about drag and drop that we're going to have to use our own variable right in here. So we're going to have to start out by setting counter to 0, set this to counter, and we're going to have to manually increase it each time we go through there. And I'm going to change the name of that variable just because I can. Rename that variable. I said I'd name it X. Darn it. I'll call it brightness. All right. So it's updated our code over here. And for those of us who are used to programming in text, the drag and drop can be a little bit inconvenient at times because we don't have full control of what's going on in the text. And in the blocks plus text function, you can't come in here and just edit the text because it's a one-way street. It takes what's in the blocks and puts it into the text. On the other hand, it helps prevent errors. So when you're new and you're starting out, it's probably simplifying things, which is good. So let's start right in here. Now, it declares some variables. Now, you don't see that in the drag and drop, but it is going to be important when we get into text-based code. We're saying, hey, computer, go find a memory location, the size of an integer variable. We're going to call it brightness. Put a 0 in it. And in here it says, oh, and while you're at it, okay, go find another memory location in your RAM, your random access memory that we can access really quickly, and store an integer size variable in it, 2 bytes. We're going to call that counter. This doesn't say to put anything in it, so if there's some random number existing in there right now, that random number stays there, okay? Um, so this is declaration of a variable, whereas this is declaring it and initializing it. I always like to initialize my variables too. You don't have to though, most of the time. So then we come into our setup routine and it says, okay, pin 9 is going to be an output. Now we come to our loop where all the excitement's going to happen. Now it starts right here. Here's our brightness equals 0. That's this command right here. Now that does nothing for the brightness of an LED. That just puts a 0 into the brightness memory location. Now you're probably thinking, Jason, didn't you just do that up here? And yes, we did, but keep in mind that loop keeps repeating. And when we come down here, we're going to keep increasing our brightness. So at some point, we need to reset that brightness to 0 if we want it to fade in and fade in and fade in and fade in. And okay, here's our counter loop right in here. Now our counter is a for loop. Everything between that squiggly bracket and the first squiggly bracket it sees after that is included in this hug right here. So think of those squiggly brackets like the hug. And right in here, we've got our AnalogWrite command, and we're going to take whatever is stored in that memory location that we've called brightness and pass it over to our AnalogWrite and say, hey, make pin 9 flash on and off really fast where it's on brightness. Okay, a number between 0 and 255. If closer it is to 255, the more often it's on, the brighter it seems to our eyes. Each time it does that, we increase the brightness just a little bit, and it loops around here and does this 255 times. Now, if we want to see that actually happening, and we don't want it to happen instantaneously, we do have to come in here, and we do have to add a bit of a delay in here. You can see me typing away in there. Wait right in here, 0.01 seconds. Okay, so this little delay loop right in here means that it will just take a little while, 255 times 10, or about 2,550 milliseconds, 2.5 seconds for it to complete this routine. So our LED should gradually fade in over the course of 2.5 seconds. Go ahead and start that simulation and watch your LED. There, it's off. And it is getting brighter and brighter and brighter. Now that's going so slow on here because this is a simulation. You can see the simulator time up here. It runs like lecture time. It just drags on and on and on and on forever. So let's take a look at how we can do this for real. Okay, start your Arduino IDE. Now you had your Arduino IDE installed last time, okay? And you can come right in here and you can wipe out all the code that's in here, save it if it was valuable, but go ahead and wipe it out and copy that code that you generated. If it's working on the simulator, it's going to work on your Arduino. Now, there's a few things to keep in mind when you're working on your own Arduino. Remember that when you plug your Arduino in, you're going to be assigned to a COM port. And if you don't know which COM port you're at, come in here and go into Device Manager, and your Device Manager window will pop up. And you'll be able to take a look in here and where it says, where it says, what's that word that I'm looking for? Ports, COM and LPT, you'll be able to take a look in there and you'll see that I've got a USB device, the CH340, which is used in many different Arduinos. Sometimes it'll just say Arduino, but you can see it tells me I'm on COM3. So if you can't find your Arduino, plug it in, take a look on here, and it'll tell you what COM port you're on. If you don't see it showing up under ports COM and LPT, then there's something wrong with how you're plugged in, and your cable's wonky, or maybe maybe you ran 100 volts through the Arduino and toasted it. It's hard to know. Okay, so here we go. We've got this in here. It's installed. We're on COM3. It says Arduino Genuino Uno, which is the right one. And let me turn this camera back on over here and shrink it down a little bit so we can see what's going on. And there we go. I've got my Arduino in right here. It's blinking away very nicely. I've got it plugged in right in here. And now you should be able to come in here and hit the upload button. It'll ask you if you want to save the file. Sure, just go ahead and save it. And now you'll see the compiling sketch message. And this little bar will fill up. And if everything goes right, you won't see any orange text down here. It tells you how many bytes of program storage space it used and how many you've got left available. And you'll notice now that we're using global variables, using 13 bytes of dynamic memory. Okay, and we've got 2035 bytes left for other variables. That's like 2K of memory, which is like 1/1000th of 2 megabytes, or 1/1,000,000th of 2 gigabytes. So yeah, it's not that much memory by modern standards, but for a microcontroller, it's pretty good. And very rarely do I ever see students use more than that. And you should now see your Arduino fading in right like so. Okay, so I've been talking at you for about 50 minutes right now. I'm going to give you a little bit of a challenge, and then I'll follow up with another video shortly. Your challenge, take this, and instead of making it fade in, make it fade out. And then make it fade in, fade out, and then wait. Fade in, fade out, wait. Fade in, fade out, wait. Fade in, fade out,